Devices that recover energy from the wind are really of two types, drag type and aerodynamic lift type. This lecture will cover the drag type of wind energy device. Thinking in a historical sense, sailors have known for millennia that the wind will push you in the direction it is headed. In that case, the force developed is due to the drag of an object exposed to the wind, in the case of a boat, the sails. The boat speed cannot exceed the wind speed. I'd like to think that experience with ships led to the development of the first wind energy devices. Devices that recover wind energy through drag are called panamones. The figure shows three types of panamone looking down from above. These are all vertical axis wind devices. The first is a cup type, that's the device A. You can see that the wind receiving element looks like a cup. The second is the paddle type, so at the end of a pole we have some type of paddle. And the third is the S type, so this is basically a bent piece of sheet metal. The wind capturing element in all these cases, you'll notice, has to go upstream as it rotates back to the starting point. So in the case of the cup type, as it moves around and comes back upstream, it has to face the wind. The designs all vary in how they try to minimize the drag on the return side. In the case of the cup type, you can see that the convex side is going upstream as opposed to the concave side going downwind, and that this side has lower drag. In the case of the paddle type, you can see that there's a screen fixed to block the wind from the paddles coming back upstream. So let's look at examples of each type. One form of cup type panamone is widely used. That's the rotating cup anemometer that is used to measure wind speed. The convex shape on the back side, so you can see right on the back side here, has less resistance to air than the concave side facing the wind. A nice feature of this type of device is that the wind direction doesn't matter. It responds to wind from any direction. I couldn't resist showing this creative practical example of a homemade device, essentially made from oil drum halves, which act as cups. So you can see the concave surface and the convex surface of these devices. Here's an example of a paddle type panamone from ancient history, in this case 9th century Persia. So this is a device, paddles with a screen. The paddles themselves consist of wood poles here, and then reeds tied to the poles to form the paddles. There's also a masonry screen right here that blocks the wind from the paddles returning back upwind, and the wind enters here where the blue arrow is and pushes these paddles, generating some force. This particular sketch shows stones for milling grain, so right here, but these devices, versions of these devices, were also used to pump water. Note that having a fixed masonry structure, a fixed screen, requires that the prevailing wind be from a consistent direction. If the wind suddenly shifts so that it's coming from the west in this orientation, you can see that the wind energy device is useless. An S-type is a variation on the cup type. You can see we have a convex surface on the return side, has lower drag than the concave surface facing the wind. A big improvement on the S-type is the Savonius rotor or split S-type. By separating the two halves of the S, you can see the offset right here. The wind deflected by the concave part of the S is deflected into the back of the convex part, and as it moves around here, it generates some pressure on the back of this and assists rotation and generates higher torque. Let's apply a bit of theory now and consider a simple paddle configuration. The wind acts normal to the paddle right here, and the paddle then rotates counterclockwise. For simplicity, we're going to screen the return paddle, so this rectangle is a very crude screen, but you get the idea. The force on the paddle is given by the formula F is equal to C sub F times 1/2 rho A times the quantity V0 minus V squared, where V0 minus V, small v, is the relative speed of the wind on the surface. The paddle characteristics are accounted for by the pressure coefficient C sub F that incorporates the paddle form and the nature of the surface. For example, concave and convex surfaces would respond differently to the wind pressure and would have different values of C sub F. With the force on the paddle, we can now find the power delivered to it. Power is simply force times paddle velocity. In this case, the paddle velocity is small v. So this is simply added then to the rest of the formula is the force. So it's also useful, again, to normalize the power expression by the upstream wind speed V0. With this change, the red circled term is the power available in the upstream wind. And the pressure coefficient, C sub F, right here, and the term in square brackets account for device-specific characteristics. Just as before, we can find the maximum power from the drag-type wind device by differentiating the quantity in square brackets and setting it equal to 0. Once again, the maximum occurs when the paddle velocity is 1/3 that of the upstream wind. In this case, however, the value of the term in square brackets is 4/27 instead of the 16/27 that is the Betz limit. Also, the power is further reduced by the coefficient C sub F. Finally, starting a wind device requires some torque. Torque is simply force times the radial distance to the paddle. Here, R is incorporated into the formula for force to get the torque. Results of torque calculation are shown here, normalized by the maximum torque to make it dimensionless. At startup, when V is equal to 0, so right here, you can see that the torque is maximized. This gives drag-type wind devices good starting characteristics. Let's summarize some key points about drag-type wind energy technology. Power is equal to force times the paddle or cup velocity. The maximum power that can be extracted from the wind by a drag-type wind device is equal to 1/2 rho times A times V0, the upstream wind cubed, times the pressure coefficient C sub F times 4/27. These devices have low performance compared to the Betz limit, as evidenced by the 4/27 coefficient compared to the 16/27 coefficient of the Betz limit. But they do have an advantage of developing relatively high starting torque. Please try the questions that follow to give you some practice with the concepts related to drag-type wind energy technology.